You know, for decades, robots have been these one-trick ponies, right? You've got a robot for welding, a robot for sorting, another one for vacuuming, and each one has its own separate, specialized brain. But what if? What if we could give them all one single unified brain? A brain that could learn to do pretty much anything just by understanding our world and our words. Well, that's the VLL revolution, and we're going to break down how it is changing absolutely everything. Imagine saying that to a robot. Seriously, think about it. Not some super specific command like pick up the green T-Rex toy, but something that requires abstract knowledge, something it's never ever heard before. And get this isn't science fiction anymore. This is the reality being built right now by a new kind of AI. And it's giving robots a power to understand our world in a way we've only ever dreamed of. And this is the magic that makes it all possible. The Vision Language Action Model, or VLA for short. It's such a beautiful, almost simple idea when you break it down. It's one single model that connects what a robot sees with its cameras to what it understands from our language to what it does with its body. Vision, language, action. That trifecta is what's finally making the dream of a general-purpose robot a reality. Okay, so how in the world did we get to this point? I mean, it didn't just happen overnight. It all really kicked off with two pioneering models that completely shattered the old rules of robotics. First up, you've got Google's RT-2, back in 2023. And honestly, this was the field's Wright brothers moment. The stroke of genius here was treating a robot's physical actions, like moving an arm to a specific spot, as if they were just words in a sentence. I mean, how clever is that? And that was revolutionary because for the very first time, it allowed them to tap into the massive knowledge of the entire internet and connect it directly to physical movement. Then, in 2024, we got the Model T moment with OpenVLA. So if RT-2 proved that flight was possible, OpenVLA built the affordable airplane that everyone could use. As the first major open-source model, it took this incredible power and put it into the hands of researchers and developers everywhere. It was a total game changer. Now, this is where it gets really, really interesting. Just look at the contrast. Google's RT-2 was this behemoth, right? 55 billion parameters, a true proof of concept that needed massive resources. But then look at OpenVLA. At just 7 billion parameters, that's nearly 8 times smaller, it actually achieved a 16.5% higher success rate. This proved that powerful robotics AI wasn't just for the tech giants anymore. This 1-2 punch is what lit the fuse. And when I say it lit a fuse, I mean it led to an absolute explosion of innovation. A true Cambrian explosion for robotics. After those pioneers laid all the groundwork, the entire field just erupted. The year 2025 is going to go down in the history books for sure. Just look at this timeline. For years, progress was steady, but, kind of slow. One model in 2022, the big one, RT-2, in 2023, a handful in 2024, and then boom! In 2025, the floodgates just burst open with over 28 new models. I mean, that is textbook exponential growth, right there on the screen. So in total, we went from just a couple of models to over 35 in the span of 3 years. It's just wild. And that created this crowded, complex, and incredibly exciting landscape. So the big question becomes, how do we even begin to make sense of it all? Well, we can actually organize this whole explosion into 3 key strategies, or what you could call pathways to intelligence. Different teams are tackling different core challenges, pushing the boundaries in their own unique ways. First up, we've got the humanoid pathway. And this is the grand challenge, right? Giving a robot with 2 arms and 2 legs that fluid, coordinated, whole body control it needs to operate in environments that were built for us humans. This is arguably the toughest nut to crack on the hardware side of things. In this table perfectly illustrates 2 totally different approaches. On one hand, you have Figure AI's Helix, which uses this cool dual-system brain, a slow, thoughtful part for cognition and a super-fast 200 Hz part for pure motor control. But on the other hand, you have NVIDIA's GR00T using what's called a frozen VLM plus adapter. So what does that mean? Basically, they take a massive pre-trained vision language model and just lock it in place. That's the frozen part. Then they add this tiny trainable adapter to specialize it just for robotics. It's an incredibly efficient way to adapt a huge model. Okay, our second path is all about dexterity. It's one thing to move a big arm around. It's another thing entirely to master the delicate touch needed for all those tasks that we do every day without even thinking about it. So let's look at a model like physical intelligence's π₀. This thing is a master of manipulation. It uses a new technique called flow matching, which, to put it simply, lets the model generate these incredibly smooth and continuous action commands instead of those jerky, discrete steps we're used to. And the result? Well, it can fold laundry, bag groceries, and assemble boxes, tasks that require a level of dexterity that was pure science fiction just a couple of years ago. Finally, we have the third crucial path, efficiency. Because look, all this incredible intelligence is useless if it takes a data center to run one robot. This pathway is all about shrinking these powerful brains to fit on affordable, accessible hardware that can actually be deployed out in the real world. And the progress here is just staggering. Remember our pioneer, RT-2? 55 billion parameters. Now compare that to a recent model called small VLA at just 450 million. That's over 100 times smaller, yet it's powerful enough to run real-time control on a single consumer graphics card, the kind you could have in your PC at home. This is what's going to make widespread adoption a reality. So what's the secret sauce driving this incredible acceleration across all these pathways? A huge part of the answer is the open source community, which has created this shared set of powerful, free building blocks that anyone can use. Yeah, you can pretty much think of it like a recipe. To build a modern VLA, you start with a powerful open-source vision model like intern VL3 to act as the eyes. You add a smart language model like Llama 4 to be the cognitive core, and then you train it all on massive open datasets of robot actions, like the OpenX embodiment dataset. This open-source ecosystem is what's allowing the field to move at such a breakneck pace. It's a classic example of standing on the shoulders of giants. All right, so let's bring it all home. What does this all mean for us? Where is this technology actually taking us? This rapid leap isn't just happening in a lab. It's paving the way for a future where intelligent robots are a part of our daily lives. Now, of course, we're not there yet. Let's be real. There are major hurdles to overcome. We have to ensure these robots are fundamentally safe to be around. They need to be way more robust to the chaos and unpredictability of the real world. And the field still needs to find the best, most standardized ways to represent and teach actions. The work is far, far from over. But the momentum is just undeniable. This quote really captures the feeling in the field right now. We are on the cusp of creating truly general-purpose robots that can understand our world, follow our instructions, and work right alongside us in our homes, our factories, and our hospitals. And that leaves us with a pretty profound question for the future, doesn't it? We're moving towards a world where robots can learn new skills not from complex code, but simply by watching a video of a human doing a task. And when that becomes commonplace, what does it mean for the nature of work, of skill, and of human endeavor itself? That's something we're all going to have to figure out together.